Hello and welcome back. So in the previous lecture we formulated the equations for one element, but we stopped at the integral sign because we don't know how to integrate. So in this lecture let's look at how to perform this integration, and we'll be doing it numerically. It's a numerical integration. So there are various ways of doing this. You might have heard about trapezoidal rule in your class, in your undergraduate class, right, or numerical methods. In FEM we use quadrature rules, which are quite more exact. There are various quadrature rules, but the Gaussian quadrature is what is used quite commonly. So let's have a look at the Gaussian quadrature. So the idea behind the Gaussian quadrature is that, let's say you have this function y is equal to f of psi defined in this domain psi equal to 0 to psi equal to 1. Okay, so if I want to numerically integrate this, the idea is that I place a set number of points in this domain, I evaluate f of psi at these points, and then I just scale these evaluations with some coefficient. Okay, and the idea is that the multiplication of that coefficient with this evaluation will give you an area, and add all of these areas for all of these points, and they should exactly describe the area under f of psi. Okay, so that's the idea. To be more precise, a polynomial of degree p in the domain can be perfectly integrated by just p plus 1 by 2 points. Okay, so a ninth order polynomial needs a minimum of 5 points. Okay, so here we are looking at first order or second order polynomials only, so we'll use a much more simpler rule. So this is called as the 2-point Gauss rule. So let's just derive this so that we understand it better. So this is our objective: find 2 points in the domain such that such that scaling them with 2 coefficients will perfectly integrate the function. Okay, so we could write this kind of an equation. So there are 2 coefficients c1, c2, 2 unknowns, and 2 more unknowns x1 and x2, which are the points. Okay, so 4 unknowns, so we will need 4 equations. Okay, so recall that the master element is typically defined from 0 to 1 or minus 1 to 1. So here I have shown the minus 1 to 1 case. So by default you will also see what's happening in 0 to 1. Okay, so this on the right hand side you have the analytical integration which you want to represent. Okay, and here you have the numerical case. Okay, so here we just plug in four functions, right? So f of x is equal to 1, f of x is equal to x, f of x is equal to x square, and x cube. Okay, so just evaluate these integrals from minus 1 to 1. Okay, you get this RHS. You could also do it from 0 to 1. It is just the area under these curves, right? And then just plug in the value of plug in x1 and x2. Okay, in f of x. Okay, so you would just get 1 x1, x1 square, x1 cube, and so on. Okay, so now basically you have these 4 equations with 4 unknowns. So just solve them and you will get these values. Okay, so these values allow us to exactly do the numerical integration by just scaling f of x1 and f of x2 with these coefficients. Okay, so how does this work for a polynomial? So you could think of since x cube is being exactly evaluated, right? So x cube plus x cube is equal to 2x cube can also be evaluated, or x cube plus x square can also be evaluated. So in principle any linear combination can be evaluated. So basically any polynomial which is up to the cubic degree can also be evaluated. So now here I have written the c1, c2, x1, x2 values at psi going from 0 to 1 as well. Okay, so this is the kind of master element we are using. So let's have a look at this. So how would we do this integration? So just these are my x1 and x2 values. So find out the value of f of psi, right? So this is like the length of the rectangle and multiplied by the breadth, which is the coefficient. Okay, so you get these 2 boxes, and what happens is that the overshoot and undershoot just cancel each other perfectly. So if I'm trying to integrate up to cubics, these will cancel exactly, and I will get an exact numerical integration. So to recap the procedure, any function f of psi, to evaluate this numerical integration, simply put psi is equal to x1, multiply by the coefficient, psi equal to x2, multiply by the second coefficient. Okay, very simple. So now these are our equations which we derived in the previous lecture. So finite element comes from a solid mechanics background. Okay, so this kind of a matrix, the matrix of unknowns, right? Rather the matrix which is multiplied by these unknowns, right? So this matrix is called as the stiffness matrix. Okay, so that's a solid mechanics terminology, and the matrix, or rather the vector on the right hand side, is called as the load vector or the force vector. So these are just some solid mechanics terminologies. This is what you can call as a local stiffness matrix, and if you assemble all of them for all of the elements, you will get a global stiffness matrix. Okay, same for the force vector as well. So now let's look at this matrix. It has 4 terms, right? So typical way of representing the stiffness matrix is using the variable k. So this entry is k11, this is k12, k22 and k23. Okay, so now let's evaluate these entries. So this is our equation for this is our first equation, right, which has basically two entries here, k11 and k12. So I have simply written them as a1 and a2 here, okay, before the integration, and after evaluating the integration by simply using the Gaussian quadrature, remember that these j terms are also a function of psi, so we have to evaluate them as well. Okay, so we can just get k11 and k12, very simple, and plug them here. Similarly, we'll also have to compute k22 and k21, right? The same procedure. Then we also have this right hand side. We have to evaluate this as well. So again, psi1 and psi2 are a function of psi. So just evaluate them, okay, using the Gaussian quadrature. So now you have your local matrix assembly, right? So for the diffusion with source and diffusion. So now we can start looking at the global matrix assembly. Okay, so let's consider this test case, right? So here for the first element you will have the local stiffness matrix as k11, k12, k22, k21 and k22. Okay, for the second element it will be k22, k23, k32 and k33. Okay, so you have a common k22 in element 1 and element 2. Okay, so because of this common node, so simply in the global matrix you just have to add this. Okay, the same would also happen if you have a force vector. Okay, so so this is your global stiffness matrix, but there are no boundary conditions. You can't solve this. This is the null matrix, right? So now let's start imposing the boundary conditions. So the very simple boundary condition that we saw was u1 is equal to 1. So this is called as a Dirichlet boundary condition, where you do not have any PDE here. You just have the equation u1 is equal to 1. Okay, there is no other equation which holds here. So we just zero out all of these rows. There is no weak form, no other integral here. Just put the diagonal entry as 1. So 1 into u1 is equal to 1. Okay, and 1 into u4 is equal to 0. Okay, just very simple, just like the FDM and FVM case. Now let's look at the Neumann boundary condition. So this is a bit complex. Here on the left hand side I have described the Dirichlet condition, the same kind of as before. Okay, on the right hand side you have this Neumann condition. So this condition basically says that du by dx is equal to a. Okay, but this is not really hard coding u1 equal to 1. That I mean u is equal to constant, that kind of condition. Okay, so the way to think about this condition is that the entire PD holds. Okay, and here you have the weak form in which you have this boundary term. Okay, so du by dx is equal to a. You just put a into this term. Okay. Then what happens is what happens to this test function. Okay, so let's try to understand this. Let's show this matrix or rather this element at the boundary. So you have two test functions here, psi1 and psi2. So only psi2 has a value of 1 at the boundary, and this term is only at the boundary. Okay, so this is simply like multiply by 1. Okay, here. So simply plug in a into this condition, okay, and you have imposed your Neumann boundary condition. Okay, so let's look at the Robin boundary condition. So this boundary condition is basically flux is equal to some function of u. So here I have just written 1 minus u. So the way to do this is for the flux, so for the constant term you do the same treatment. Okay, and for u here you are just looking at the boundary point. Okay, so this condition only holds at the boundary, so you are only looking at u4 here. Okay, so simply you have to take u4 on this side. Again the same logic that you are multiplying by the test function psi2. Okay, So and psi2 is just 1 here, and you are only looking at the imposition here. Okay, so just add 1 onto this side. Okay, so this is the imposition of the Robin condition. So now we have looked at the global matrix assembly. We have also looked at the boundary conditions. So now we are in a position to actually go for the solution. Okay, so this is what we'll look at in the next lecture. I thank you for your attention, and I'll meet you again.